Okay.
Okay.
All right, I'll close the door. Oh, hello. Welcome back to another session of our learning class. Here, we're going to learn another aspect of physics that is important to technology. So, today, we'll talk about chemical equilibrium and chemical potential, which is a way to quantify chemical equilibrium and like to predict what is going to happen for a chemical process, which can be a chemical reaction, but it's also important for devices that have chemistry, but like electrochemistry is one important application of chemical equilibrium. Electrochemistry and batteries is a part of electrochemistry. Fuel cells are part of electrochemistry, and other classical reactions also have this behavior in terms of the direction the reaction will go in and such. Okay, so one thing that we should first introduce would be Gibbs free energy, which is a thermodynamic parameter. They call them free energies because it's just some way to relate. It's like one step above the actual tangible variables and state variables that a system has. Whether you're talking about some molecules, a beaker of some solution, flow in some big engineering applications. We all know everything has energy, and how do you quantify energy? By some tangible state variables like velocity, temperature, pressure, all of those. Then there's some theories to link those energies, those state variables, to other state variables like free energies. So that's what Gibbs free energy is starting with. But then you build the Gibbs free energy by a competition between entropy and enthalpy. So enthalpy is H, entropy is S, and you may remember some theories to relate enthalpy to temperature and entropy to temperature and pressure. So that's what Gibbs free energy is based on. And then if you were to take the change in Gibbs free energy for a process like a chemical reaction, you can relate that to enthalpy and entropy. Most of the time you analyze this at a constant temperature, so you would have this T, there's no change in temperature, but there's a change in enthalpy and enthalpy from the beginning state to the other state. And as we may remember, in terms of thermodynamic properties, a lot of the study of thermodynamics is where is the universe happy? Like what is stable in terms of what happens spontaneously, and if you leave a system at this state, where is nature going to take it eventually? And the way to for entropy is that what nature likes is that if you have a process, you would like that, nature would like that delta S is greater than 0. So you have more entropy in the end. Nature likes this, delta S greater than 0. And for enthalpy change, it likes for there to be less enthalpy at the end. And similar for delta G. If you were to look at a process and say, what does nature want to do? Nature would rather have the products be negative. The products have less Gibbs free energy than the starting point. And because of that, that's the most stable condition, where if you go from one state to the next state, the nature will take it towards the direction of the smaller free energy at the end. Same with enthalpy, the opposite for entropy. So that's what delta G is. It's a compromise between these. It wants to increase entropy, it wants to decrease enthalpy. So this is a way to quantify that competition. So if we were to, so that's a general idea. Let's apply it to combustion, which is burning a fuel to get an enthalpy change, negative, such that the products are much less enthalpy in terms of the bonds, chemical enthalpy, at the end. And when that, because of that, that energy goes towards increasing the temperature of those products. The bond energy is smaller, but the temperature is higher, and it gives you a higher sensible enthalpy, and then you can use that for mechanical work. So consider combustion, and when you consider combustion, the most general, simplified description of combustion, of methane, let's say, methane, CH4 plus 2 molecular oxygens in air. So air has some nitrogen, mostly nitrogen, some oxygen. So if we were to do this balance, you would have, for every 2 oxygen molecules, there's 2 times 3.76 nitrogen molecules, because that's a proportion, 1 oxygen molecule to 3.76 nitrogen molecules. And if you were to burn methane, you need 2 oxygens if you were to say, I'm going to make CO2 plus 2 waters, 2 H2Os. So that would balance out. Yeah. Then this nitrogen that's left over in terms of it doesn't do much. In real life, it may react a little bit, but in this energy balance, you have to consider that the products are hotter because of this lower chemical bonds energy, but the nitrogen takes in some of that energy. So it has some mass, some molecules that affect the energy balance thermally. So that's our most conventional, simplified one-step combustion reaction, which is a pretty accurate way to describe it. But an even more accurate way to describe it would be to say that, and because of equilibrium effects, this is not the only pathway this reaction can take. What we do observe in real life combustion, accounting for the details of the thermodynamics, is that if you were to burn methane in air, another pathway that can happen would be that you would not fully oxidize this to CO2, and you would not fully oxidize this to H2O. Instead, you would form CO and hydrogen molecule instead of hydrogen oxide. That would leave you with 1 oxygen left. So if we balance that, it's 1.5, and then the nitrogen. So there is a lot of chemical bond energy between CO and CO2. This is a more exothermic, so you would have more energy change if you were to go from CH4 to CO2. There's a bigger delta H there. And because we're only going to CO and H2, that's less bond chemical enthalpy change. So this would be more delta H. This would be less delta H. But if we remember entropy, entropy is favoring on the molecular scale more multiplicity, a higher probability case in terms of what is more, organized. I don't like to use that with entropy, but sometimes it works because it's not only organization and chaos and disorder. It's not only that. It's the disorder on a molecular scale, and it's the probabilities and multiplicity. So here, there's more molecules. There's one molecule of CO2, 2 molecules of water, and then the nitrogen. Here, there's 1 molecule of CO, 2 molecules of H2, plus another half molecule of O2. So there's more molecules on this end. That means there's more multiple ways to make this happen. There's more numbers here. So this is actually more delta S. It's the entropy increased more. More delta S, and so there's less molecules here, so it's less delta S. So that's going to form a competition between these two pathways. How do we quantify that competition? We use Gibbs free energy, and how does that look? I'll show you how that looks graphically. So if you were to keep track of this process, the Gibbs free energy as a function of temperature and pressure equals, we're just going to consider the temperature effect. This will be the temperature times S. And you would plot that. So this is a chemical reaction, so it changes as you go from reactants to products. So what we're going to say is on this axis, the origin, you're going to say that there's no reaction yet. It's 100% fuel air, 100% reactants. Here, it's 100% products. So when you're going across there from the origin to going away from the origin on the x-axis, somewhere in between there, it's a mixture of products and reactants. In the same mix, if you have this in a closed chamber, there's a mixture of some methane there still and some oxygen there still. So you can do this with any reaction. And for the combustion reaction, it's exothermic, meaning that the enthalpy of the bonds of the products of CO2 and water is less than what you started with. So it would be some progression going down from high enthalpy at your 100% reactants to, if you go to the full products, you'll have less enthalpy at the end. So this would be the enthalpy as a function of temperature. But for the other process, the enthalpy, so both of them, the enthalpy increases, but if you look at this one, there's more entropy. So in this one, it'll go higher. You'll start at some low entropy state. So if we say that this is the entropy contribution, we see that that one goes higher. So the Gibbs free energy, what that is doing is it's finding it's literally the linear combination of those. And if we were to plot this graphically, it'll look something like this, the Gibbs free energy. So that's the showing. I'm showing that this is what the enthalpy is doing. This is what the entropy is doing, and when you add those together, you get this net curve here. So what happens is, if we want to determine which one wins, well, both win in the sense that there's a compromise, not one of those wins. If the products win, you would have a Gibbs free energy here. If the reactants win, you would have a Gibbs free energy here. But what nature likes to do is to minimize the change in Gibbs free energy. So what actually is going to happen, and if you consider the equilibrium, that there's going to be a mixture at the end that's still has some reactants and hasn't gone fully to products, just because that's how the energy levels balance out between enthalpy and entropy. So this is a minimum. So this is one way to define chemical equilibrium. So if we define this x-axis to be reaction progress, 0 is 100% reactants, 100 is 100% products, then we can have this new variable to say that, well, if this is a minimum here, this is a slope going in this direction, this is a slope going in this direction, but here the slope is 0. That's one way to define the minimum. So mathematically, you would say that the minimum Gibbs free energy as a function of this reaction progress equals 0 at chemical equilibrium. So applying it to this combustion reaction, combustion products is a mixture of 1 and 2. Because of this equilibrium effect, that this has a bigger entropy change in the positive, which nature likes. This is a bigger enthalpy change in the negative, which nature likes. So as a compromise, at some point in the middle, it's going to happen someplace in the middle, and what that means for this combustion system is that it's going to be both 1 and 2 contributing to the final result. So that's for the combustion reaction. Now we can do a little bit more general analysis for all chemical reactions. This is useful for any set of reactants, any set of products. So let me erase this stuff for the combustion. So also happens, it's harder to define for bio, but bio has chemistry at its heart in terms of the actual bottom line process interactions. Okay, so for general reactions, you can say that the reactants, if you would have put a list, I'll make an example earlier, but let's say each reactant has a coefficient in front of it, let's call it nu, and then each reactant has an identity, let's call it I, like a molecular formula, is balanced by the product. Let's call it, let's put a dash, little apostrophe here. So this is reactants. This is products, So for example, you can have two C's reacting with one D to form one E plus one F. Put a 1 here. That's one possible reaction. And that the 2 is the nu here. So there's one, that's the coefficient for the D. So that's one example of how to, this is a general way to write that. What you would say is that the Gibbs free energy of this system, this whole container of where this reaction is going to take place as a function of temperature and pressure, equals the sum of everything, which would be all of the reactants. Depends on how much there are. You can quantify that with this coefficient. And then, so this would be the molar. It would be, instead of big G, this would be Gibbs free energy per mole. Then you multiply it by this amount of moles you have to get you the big G. So that would be one part of it, but then you have to, if this is one system we are analyzing, it's all in the same system, the same chamber. So it would be, did I say? Oh, I should have said N here, sorry. N, it's per mole. It's related, but let's make it more general. So these are the products. So that would be the Gibbs free energy broken down into all the contributions. Each of them contribute. So then we apply this, this definition that it's some minimum in this function. So we can also say that delta G, if we take mathematically, we could just get rid of this reaction variable and just say that delta dg dp equals 0. Or skip the step here. Let's bring that back. So we can say that applying that to this general relationship, you would get dg equals, then plug in this here, you would get contribution of the reactants, but bringing in this reactant variable, it'll be the change in the moles as you progress. So this will be saying that as the reaction progresses, the number of the molecules changes. The moles of the reaction change, that's in the chamber changes. That's what this is saying. And same thing with the products. As the reaction progresses, moves back or forward, the change in the products, concentrations or numbers is going to change as well. That's what this is saying. And then at equilibrium, this equals 0 at equilibrium. So if this equals 0, then we can get rid of this, bring all of this to over here. So this simplifies the equation. We can say that because of this, at equilibrium, that just the summations so this will be just the coefficient in front of the moles, in front of each molecular species. This is reactants. This is products. at equilibrium. Okay. So at equilibrium, you would break up each contribution of each component into its individual Gibbs free energy. You weight it by how many is there. If it's 2 there, then you put there's double the count, and so forth. So then we can apply these other thermodynamic concentrations or principles. So I'll erase this over here. What should I erase? I'll erase this. So Gibbs free energy is H minus Ts. So I won't derive it, but by combining the known combined first and second law of thermodynamics, you can say that the differential change in enthalpy, I'll write it big, differential change in enthalpy equals TdS, that's the second law, and plugged into the first law here. That's one way of writing the first and second law combined. Then, if we remember that, you can express the enthalpy in terms of a specific heat, Cp, and temperature. So this is an abstract energy. These are tangible parameters for each material in each system. And then you could also write that in general, the delta S equals some reference condition that you can write in the table plus R universal gas law constant. Oh, it's minus. And the partial pressure. So by combining all of those classical thermodynamic relationships, you can write that for one component, the Gibbs free energy for one component in a mixture as a function of temperature and pressure is some standard Gibbs free energy that you can look up in a table minus the gas constant times temperature times this pressure ratio. So there's a couple things about this equation. This means means 1 atmosphere, like standard atmospheric pressure. PI is partial pressure, meaning that if everything's in the gas phase, each molecule contributes to this total pressure by this individual. The total pressure is the sum of all these individual contributions, which is related to the mole fraction. So it's a way it's a concentration measurement. So then, eventually, so this is, you get the total Gibbs free energy system from each contribution. And where should I erase? Yeah, no. So now, instead of expressing the Gibbs free energy in terms of enthalpy and entropy, we now have the Gibbs free energy in terms of pressures and temperatures and a table value, which is good. It's easier to use that way. It's more direct. Like if we know the temperature, we know the pressure, we can calculate the Gibbs free energy and find the standard enthalpy in the table for the given temperature. So now it's more direct analysis, but it's based on the competition of enthalpy and entropy. So we're now define another parameter called chemical potential. I just realized chemical equilibrium and chemical equilibrium. This should be chemical potential. I'm glad I finally realized that. Chemical equilibrium and chemical potential. So speaking of which, chemical potential is another way to quantify Gibbs free energy. It's basically almost the same thing. I didn't write the, was it here? Yeah. So the chemical potential is a new symbol called mu, and it's usually expressed in terms of each component only. It's what you do, it's related to this discussion of the reaction progress. It's saying that when it's the delta G of the system with respect to the change in moles of this component when everything else is constant. So for a constant temperature, pressure, and keeping the other moles the same that are not I. So what it's saying is that, this is the definition, is that if you're undergoing a reaction process, when this reaction proceeds back or forward, the molecule is going to change numbers. It's going to be consumed or produced based on whether the reaction goes forward or backward. And so what the chemical potential is saying is that as this moves, gets produced or consumed, how does the Gibbs free energy of the system change? So that while the constant temperature and pressure, but it's saying that you keep all of the other components in the mixture constant, and you just change this one component in or out. It's kind of abstract because you cannot change one component without affecting the others, but that's how the reference definition is. So it's going back and forth. How does the Gibbs free energy change? That's what the chemical potential is keeping track of. And then, so by skipping some steps to show that we know kind of where this pressure correction comes from. And if it's a mixture, if we're talking about each component, it depends upon the partial pressure of the component, like the concentration of that component. You can do a similar expression for the chemical potential to say that if this is in your mixture, the chemical potential of that one component is related to the standard potential at 1 atmosphere that you can find in a table, and at some reference temperature, plus RT ln of this chemical activity. So this AI is called chemical activity. And so I'll erase this over here. So chemical activity depends on, or how you quantify it depends on the phases basically. For gas phase, ideal gas, AI equals the partial pressure of that component over the total pressure. For non-ideal gas, there's a correction factor. It's some parameter called the fugacity correcting this partial pressure. And then if you had a concentration, a solution, meaning that it's a liquid with these different components in there, there's also a correction factor. So this is the concentration. All of these are concentrations, and is fugacity, where it's a value between, it's a correction factor between 0 and 1. And And so if we're talking about ideal gas, we're going to have this partial pressure relationship. So, skipping some more steps, we can say that at equilibrium, this all equals 0. So the Gibbs free energy does not equal 0, but the change in Gibbs free energy equals 0. So we can write this differently. We can say that, skipping some steps, if we had a reaction at some temperature and pressure, the Gibbs free energy change of the reaction at equilibrium equals negative R, the related to the ideal gas constant, times this ratio here. And in terms of gas phase, times Kc or Kp. The Kc would be, let's just say Kc, yeah, Kp, or for, so this is solution, C as in concentrations, this is gas phase at chemical equilibrium, and that's what this is. It's an equilibrium constant. So where Kp is the equilibrium constant. And what the equilibrium constant tells you is the concentrations. So this is, I don't know if you remember these symbols. It's not a summation, but it's a multiplication. So for each component in your mixture, you would raise the partial pressure to the to whatever stoichiometric coefficient. So the reactants are at the bottom. So for this reaction here, it will be, let's say this is reaction 3, the Kp of this 3 reaction here is, let's see, the partial pressure of E raised to the 1 to the, and the times the partial pressure of F raised to the 1 over the partial pressure of the reactants of C raised to the 1. Oh, 2, I mean. So that has a 2 of the coefficient, so that's raised to the 2 here. And that's what you use it for. You say, okay, this equilibrium constant will give me an idea of the concentrations that are in this mixture. And it gives you this ratio. It doesn't give you the individual concentrations, it just gives you the ratio. And then you can look this up from the table many times. So that would give you one way to say, at equilibrium, what are my concentrations? Well, you can sometimes you can find these equilibrium constants if this reaction is defined clearly and it's a common reaction. You might be able to find this in tables. There are theories to help you find it from first principles. You might be able to find the Gibbs free energy, the delta G of this reaction. And then based on the temperature and this relationship here, you might be able to find that. So, and then you could also express it in terms of the chemical potential as well. Yeah, so sometimes you see it in terms of chemical potential, but this is the idea for that. And for combustion, this is in either a non-ideal or ideal gas. For solutions, it's this expression, and electrochemistry is in solutions. You have some either some aqueous electrolyte to keep the battery running, or you have some organic electrolyte to get the battery running, and the concentrations of all that determine the chemical potential. And fuel cells. So batteries, they don't only depend on thermodynamics, but if you don't design the battery or the fuel cell around stable, not necessarily stable, but things that Mother Nature play with the direction that Mother Nature likes. The whole idea of a battery is that depending on the energy levels of your anode and your cathode, you'll get your electrons to flow one direction or the other. And that's another way of quantifying that is by the Gibbs free energy or standard reduction tables. Either way, it's the similar principles. It's all about where Mother Nature is happy. How do you quantify where Mother Nature is happy is by chemical potential, chemical equilibrium, Gibbs free energy. They're all related. Okay, so that's all I had. Thank you. I'll see you guys next time.